Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, all right. I'm going to talk about networks in the sense of semantic networks and how you look at data, in particular publication data with them. But the whole schema goes to a lot of things. These kind of networks, the social network things, really, 11% of all the papers last year in the Physical Review E were about these kind of systems. The $200 billion algorithm, of course, they have commercial value. PageRank is simply eigenvector centrality, and the idea to do that on the interconnectivity between websites is worth what Google is worth, I guess. You all know about the 6 degrees of separation stuff and the small world theory. Well, my Bacon number is 4, my Erdos number is 3, and my Gray number is 2, which means that I wrote a paper with Alex Saleh, and Alex Saleh has written, of course, a paper with Jim Gray. Yeah, it's, the name of the film is So Many Galaxies, So Little Time, but the producer director of that film is a real, Hollywood film person. Well, all right. You can do a lot with this kind of data. This is a friendship network. It's a pretty famous diagram. The dots are people. They're students, and they have properties. The lines are friendships between people, and although I may be friends with you, you're not necessarily friends with me, etc. They're directed links. Here you can see the white kids, the black kids, and the junior high and the senior high kids. And of course, making that graph was a real tour de force. The data doesn't just come that way. Well, objects have properties. But the question can be, which is the object and which is the property? Do authors have papers or do papers have authors? Well, obviously both. And once you start having weighted links, which is papers have multiple authors, authors have multiple papers, you start going into normal factor analysis and classification mathematics. So there's now a large set of mathematical tools and techniques to deal with these kind of data. Well, here's an example of a bipartite network. And of course I'm talking about multipartite networks, but every one of these has got a zillion things in it, as I'm sure you've recognized. We'll see anyway through the talk. Papers are assigned keywords. Keywords, of course, are kind of semantic tag. I should point out here that they are assigned by people. Which says human judgment is involved. And here, the whole nature of what I'm going to show at the end of the talk is concentrating and capturing human judgments in order to make recommendations. And but you can build networks of keywords based on the papers that link to them, and you can build networks of papers based on the keywords they link to. That's what this diagram is for the astronomy literature. Edwin Hennigan built this diagram. But this is a network of astronomy papers as linked by keywords using the Roswell-Bergstrom algorithm, which I think is the best network clustering algorithm currently. Well, before I get into the stuff that I actually do, which is play with the literature, I'm going to talk about Pavlos and what Pavlos is doing. Pavlos runs the Time Series Center at Harvard. And time series are basically sets of observations of stars, galaxies, quasars, other things, but mostly stars. And stars are objects and have properties, and the observations of them are objects with properties made with spectrographs or photometers at a place, in a bandpass, etc. And series of observations are also an object, and that leads to a time series. There's a set of objects becomes an object. And what Pavlos has done is he has created a pretty clever similarity measure for time series. So he can go in and take a time series and look for similar time series. And that says, basically, because these time series are associated with stars, he's finding similar stars in some measure. Well, okay, he can take papers on these similar stars, and he can ask, are there any papers about these stars? The Simbad database has those if they exist. And then you can take those papers, you can get the keywords from ADS, and that gives you, add them all together and see which ones come on top. It gives you a proto-classification for the star, and he has over 1 billion time series. So finding classification for a random star is not a trivial matter, since he wants to do it programmatically. Well, now back to papers. Papers have lots of characteristics. They have lots of other objects, if you will, that are associated with them. They have authors. They have readers. The readers have properties. They could be at Carnegie Mellon University. They could be in China, for instance. They have keywords. They have words. That's what latent semantic indexing really is. It's just manipulating the words. They come from organizations. The Center for Astrophysics, where I work, has a quarterly publication that is all the papers that went there. It only goes to our administrators, but okay, they're the ones who decide the money. Journals. References are just papers, but they're in the back of papers. You can view them something differently. They have dates. They have data associated with them, all the problems of data. And they're associated with astronomical objects, like some particular star or galaxy. I'll show that a little later, too. Well, okay. You use this stuff to search. And different searches from the same query can give very different results. And there really is no best answer. There is no best search. It depends on what you're doing. Here, for example, are two different sets. These are the obsolescence diagrams for two different query engines on the same data. These are the main astronomy journals. The queries were done in October 2007. And this is the log scale on the side. And this is the frequency with which these articles were read as a function of their publication date through the ADS interface, using only people who came to the ADS interface more than 15 times in a month or something like that, and came through Google. Well, this is a steeply declining exponential, and this is basically flat. Different query interfaces really do give different results. This is basically the same plot, except the bottom one is Google Scholar, and I've compared it now against the citation rate to those same papers and the total citations to those same papers. And you'll note the ADS interface use matches the citation rate, whereas the Google Scholar interface use matches the total citations very well in shape, not in number. These are normalized to 1 somewhere out here. Well, what do you do when you search? You're basically filtering on some properties, then you rank on some properties. But what properties? What's the goal? Well, the user defines the goal in a search, or there's some sort of default, but basically you decide what search engine to use then. For an example, weak cleansing. Weak cleansing is a pretty common concept now. There are a lot of papers written about weak cleansing, weak gravitational lensing. There are more than 2,000 papers in ADS that contain that phrase in their abstract. If you just make a query on weak cleansing, how do you decide what to show? What properties do you rank on? Well, if the user decides, this is the normal ADS interface, every astronomer uses this pretty much every day. I'll make a query to show you how, if you know what you're doing, you get what you want. Here I say weak lensing. I'll go down and say I want data about weak lensing, so I'm only taking papers that have links to data. And I'm going to sort it oldest first by date. And if I do that, on top I get the Hubble Deep Field observing proposal, which is a pretty nifty thing to find, but you kind of have to know what you're doing to do that. Different goals require different searches, and if the user just decides on the goal, you'll get different results if you do it right. And here is our topic search, and again I'm going to take weak lensing, and there are 6 different types of queries we do here, and I'll go through what all 6 do. The first one, most relevant, is basically the secret sauce. It's our equivalent to Google. It's if you put in this phrase, these are probably the best guess at what you might want to read if you don't know any better as to what you're doing. Of course, only professional astronomers use ADS, so we're not really looking to find educational materials for the general public this way. The next one is most recent, and that's the standard way most search engines work for academia. You get the latest paper that exactly matches what you're looking for, and most people, in fact, are looking for papers by an author. People normally know what they're doing, know what they're looking for, and come in and find the latest paper by, I don't know, Alex Soleil. The next one, most important, this is actually really most cited, and since we are the ones who did this first, I'll describe in a half a sentence what it is. You take the papers that contain the phrase weak lensing, and then you sort them by their number of citations. And we've been doing this for almost 20 years. Anyway, if you compare this to the eigenvector centrality or PageRank, they're very similar results. It's why when you look at Google Scholar, it's basically the same as the total citations. I think that Phil Davis has shown, who's at Cornell University, has shown for the academic journals that if you rank them by PageRank and you rank them by total citations, the two rankings are not significantly different. So we figure we don't really need to go through all the network calculations to get something like this. It just comes out trivially. Well, the second set of queries are really more network-based, and we use the properties of the results of an initial query to get a new query. For instance, people who bought these books also bought, not this book necessarily, these books. You have an ensemble of books, and you take all the people who bought them, and you find all the books they read, and you rank them. We have been doing this since 1996. Amazon has been doing it since 1998. Anyway, here's one, most popular. How you do this is you get the most recent 200 papers containing the phrase weak lensing. You find all the people who've read any of those papers within the last 3 months. You find all the papers read by those people in the last 3 months, and you sort by frequency of use. And that gets popular papers, hot papers, pretty much on this subject. And that works pretty well. I won't show you the results of these. Basically, you need to be a subject matter expert to understand how well it works. I'll just say, normally this stuff works very well. Most useful, this is interesting. It's interesting to compare it to most important, because they're both citation-based. You get the most relevant 200 papers. That uses the secret sauce, but the most recent works pretty much exactly the same way and gets very similar results. And then you find all the papers cited in the reference sections of those papers, and you sort by frequency. So you get the ones that are referenced the most by these 200 papers. Think about this in terms of trust networks. We are taking the most relevant 200 papers containing some phrase, and we're trusting those papers to pick papers that are going to be useful. And now most instructive. This one works very well. It's the one I recommend people think of if they're trying to remember any one thing from here. But you take the most important or most cited 200 papers that contain the phrase, then you find all the papers that cite any of those papers. And you sort by number of papers cited, and the ones that cite the largest number, they're going to be review articles on weak lensing. And in fact, if you do it, this is the one I will show. The top 4 or 5, all are review articles in weak lensing in review journals. Schneider's is a continuation of his earlier review article that he published in some conference proceeding somewhere. Okay, enough for search. Let's go on to browsing. Browsing is user-mediated, but it's not intended to solve a specific need. This is our current browse system. We put it out, I think, 8 years ago. These are all different queries. This one, and this one are normal queries, just subject matter queries. And then this one, this one, this one, this one, and this one are second-order queries of one of the sorts that I just showed you. I won't describe it at all. Here's another browse system we have out. This one's hardly used, although it's sort of nifty. We've run the Roosevelt-Bergstrom algorithm on the co-citation graph of the astronomy literature. And we have taken the clusters, we've given them names based on keyword frequency inside the papers in the clusters. And then we've run this little gizmo. If you click on one of these, it's a flash application. If you click on one of these things, it all moves around and the lines move around. These things are connected to these other things by the lines, and the width of the line shows the strength of the connection, and the arrows show the direction of the connection. They're not all symmetric. Well, anyway, those two things The first one has been around for a long time. The second one we may or may not try and figure out how to get people to use. People don't really use. But what I'm about to show you, we are going to implement probably in the spring when we change the user format, the user interface. But we're going to have a browse system based on a hierarchical classification of users. So how we do this, we're going to take all the papers in astronomy, and we're going to create a reference vector from these papers, which is simply the papers in astronomy that they reference. Now we're going to take all the readers, and we're going to create a vector for each reader, which is the sum of all of the paper vectors that they have read. So it's based on the shared papers referenced by read papers, right? So every single paper will have a vector which has as many entries as it has references in the back, and then people will be the sum of all of those, and we normalize and all that kind of stuff. But then we take these people, trimming dimensions which don't really have very many, so papers which aren't cited more than a few times. And we cluster that stuff by normal hierarchical clustering means, and we get a subcluster, and we do that again, and we get a subcluster, and then at every stage, from the top to the bottom, we have a group of users. With this group of users, we have basically a filtered set of people who we trust to describe some subject matter. Well, we take them, we get the most read papers by these guys, take the top 30, and then resort it by date. So we get basically very well read recent papers. And we just iterate on that. And here's the top one, which is all 6,000 heavy users in astronomy. And if we, let me go back one, let's see, that way, go back. And up here I cut them up into 10 different subject matter categories. This spans what astronomers actually read. And I'm going to choose Milky Way dwarf galaxies just to go down. And okay, these are the hottest papers among the group of 600 people in the Milky Way dwarf galaxy cluster of readers. And if you look at this and are expert enough to figure it out, they really are all about that. And then I broke it up into 6 more clusters of about 100 people each. Some are 70, some are 150. And I'll choose Milky Way globular clusters. They all work. Indeed, these are all about Milky Way globular clusters. There are lots of papers on it simply by construction, by the way we created the system. It's what people actually read. All right, finally, I'm going to get into recommender systems where there's no user interaction whatsoever. So we have to understand what the user's current need is. And one way to do that is just that the user is currently reading an article. We could also use the use history of the user, or of course we can figure out similar users and their behaviors, but we're not doing that yet. We'll put this out also in the spring with the revamp of the user interface. This is a complicated process, and how much time do I have? Lots? Oh, okay. I have plenty of time. Okay, so I'll go through it. First, we do it by a similar method to the way we did it before, except instead of using the papers, we're going to use the keywords in the papers. So first we create a system of normalized keywords. There are about 5,000 standard keywords in astronomy that basically all the journals have agreed on, but many of them are rarely used, and some of them have different spellings and things like that. So we had to normalize these. So it's down to about 1,000. Edwin Hennigan did all that work. It's actually a lot of grunt work. So we now have a 991, or I'm going to call it 1,000, dimensional vector which describes each paper where every one has got something like 4 keywords. So it's 0 or 1 in everything, but there are about 4 ones. But for every paper we go further than that, and we make the paper vector be the sum of all the papers that that paper references. And a paper typically references on the order of 20 papers, and every one has on the order of 4 keywords. So every paper vector is the sum of it has about 80 different data elements in the vector. And we normalize these, of course. Well, the next thing we do is we create user vectors, and we are creating it on 6 months worth of information. So a typical user has read about 150 papers in that time in the system. We actually cut it, so we're using users who've read between 100 and 300 papers. So every user vector, which is just the mean of the papers the user has read, has got about 10,000 different keyword individual measures in it. And remember, every keyword is an individual measure of what it's about, as done by a person who's assigned the keyword to the document. Now that we have this 6,000, about 6,000 astronomers who use the system regularly, versus 1,000-dimensional vector, we run a singular value decomposition on it, and that gets out so and so many significant vectors. We take 50. You can think of these as the vectors of the mind in the Thurstone sense, that these are orthogonal people, orthogonal readers. Nobody is really an orthogonal perfect person. Everybody is sort of a combination of these things. But 50 is actually sort of plenty. More than 80 is certainly more than enough, but we took 50. It looks good. Oh, right. And then we fit the papers down to this lower dimensional space. Once we have the fit, now we have 60 or 70,000 papers. We've done the most recent 10 years of papers to build the space. It's not necessary to use all the papers you're going to use in building the space. So we then cluster the papers, which are now 50 by 50 dimensional vectors, using just a normal hierarchical clustering method. And we do it, I took 64 clusters this time because there are about 1,000 papers per cluster, and that's a reasonable thing. And then we do a singular value decomposition on each of the 64 subspaces. So we now have 64 little decompositions. And inside each subspace, we fit papers in each cluster to the most significant vectors, and 5 is perfectly enough. And you can do all that in advance. And you want to do it in advance because you want it to be fast when you actually do it, because it's a real-time thing. People aren't asking for it, so they're not willing to wait. So now for each paper being read, you go into this space, and it's just a decision tree to find where it is. And you find the 40 closest papers or so. These are all arbitrary numbers. In the relevant subspace, and now you have a set of papers that are really very much like the paper being read. And you can use these to increase the signal to noise of the recommender operators. So here are recommender operators, and I'll just go through an example and tell you what they are when I go through it. For a paper which is on the X-ray variability of accreting black holes, the paper that is read most after somebody read one of the 40 papers that are nearby this paper is this paper, which is about accreting black holes, actually, in spin parameters, just exactly what the previous paper was about. You can take before and after, so the papers that are either read immediately before and after, and add those two lists together. And the top of that list, in terms of most read, is this paper, which is also exactly about the same subject. Well, you can take the people who read any of those 40 papers, and you can say, what papers have they been reading recently? And in the same trick as with the browse system, you can cut that at 30 and sort it on date so that you get the most recent well-read paper, and that's this one. And this is the one of all these which isn't directly about spinning black holes. But it is about black holes and presumably interesting to the people who are reading it. And you can get the paper that those people read the most before you resort it on date. There is one on top, and that's this paper, and that's also about accreting black holes. The paper that those 40 papers cite the most is this paper, which is a classic paper by Sakaya and Sonyaev. This paper cites the largest number of those 40 papers, and this paper has the most shared astronomical objects. Those 40 papers refer to stars or galaxies. These are black holes. Well, other papers refer to those. And if you look in the Simbad database, you can take the 40 papers, you can find what papers refer to the objects in those papers. You can then find which of those papers refer to the largest number of papers in those 40 papers, of objects in those 40 papers, and you sort on it, and this is number 2 in the list. Number 1 in the list is actually this one, which you already had. and calculated through an entirely different means, having nothing to do with the objects. And when you're done, all you have is what our new abstract page is going to look like, and you have these things over here, which people may or may not ever want to click on. But if a percent or so of the people click on it, this stuff is used so often. I mean, there's something like 50 million of these a year put out. If 1% of the people save a minute, it's completely worth the effort that goes into it. Okay. We live in a very densely interconnected world, and it's getting more and more densely interconnected all the time. The semantic interlinking of literature with data through things like ORE and the virtual observatory is forcing this to happen. The connecting tools and procedures with each other and the results through workflows and other kinds of technologies is making it so that everything is densely interconnected through a very complex set of parameters and links. And what we're talking about here is really knowledge engineering. There is no best bridge or building design. It's been centuries, millennia, that people have been building bridges and buildings, and they still design different ones. And the same is going to be true here. We are, looking at things to make them right. These are, you doubtless noticed, these are all totally ad hoc decisions as to how to build something. Well, okay, that's the way it is, and what we are basically doing is we are building the little pathways in our intelligent brain, the global network. It's a commonplace thing. This is from a workshop in honor of Francis Highlighton, who is one of the people who created this global brain idea, but it's a rather old concept that human society is a superorganism, and that our electronic databases and communication systems are building the brain of that superorganism. Well, I would object a little bit. I think it's building basically the lizard brain, and the outside thinking part, that's still us. We're connected to this. And what we're doing now is we're building the connections between the lizard brain and our own way of thinking. Okay, thank you. That's just our latest poster.
Infrastructure, so that instead of astronomy, I'd like to go through, I don't know, biodiversity or whatever?
Well, it really is based on simply having the literature available and the information on the readership of the literature. So, for instance, if you owned PubMed, you could do it for the content of PubMed. Having the citations and references is a very important thing to be able to do this, but also having the reads.
Okay, let's take another question.
This may be a naive question. So one of the approaches you talked about, you pick up 200 top papers and then use the citations that those papers
right.
have to rank them. Now, some of the papers might be citing a bad result multiple number of times. So if you don't take the context of citation, how does it affect your ranking?
In practice, I don't think that's an issue. I think that's theoretically so. But if you aren't capable of finding that something is a bad result, you don't belong doing this anyway.
No. So in the paper, somebody says, no, this result was not valid, and that is repeatedly cited.
Right.
In biomedicine, it's often done that some traditional approaches are cited as, no, that's not the way to treat this, or that's not the way to approach this, and that actually is...
Yeah, but you know that when you're looking at it, right?
No, in your ranking algorithm...
Yeah, when you use the ranking algorithm, you know the limitations of citations.
Oh,
I mean, it's,
algorithms that take the context of citation, they do the abstract or the content, natural language processing, and take the context of citation into account when they are ranking these.
Right, if you want to go to all that trouble, which I don't.
Okay, we have to stop because the other session starts right now. Thank you very much.
Thank you.